Hi, in this video, we want to take a look at validation of logistic regression models. Okay, so logistic regression is a type of machine learning model. And when we are set the goal of predicting the future with a model, whether it's logistic regression or another type of model like linear regression or random forest, stochastic gradient boosting, neural network, whatever it is, we want to have a good idea of will our model perform well, right? Before we launch the model. Now, the approach I'm going to talk about here is that we're primarily concerned with predictions. So we might build a model for inference, we might try to understand some things, but for this video, really we're focused on understanding the future, seeing what's going to happen. Our goal is to have a crystal ball that will predict things for us. So we need to know, do I have a good model? Yes or no, or like somewhere in between. Okay, so how we typically do this in machine learning is that we're going to partition our data into three different subsets. And so when I say partition, each observation that I have goes into one of three subsets, and they go into exactly one, and we don't leave anything out for this. So we're going to have three subsets: training, validation, and test. Our training data is the data we use to build our model with. We actually fit the model with. Our validation set is the data set that we're going to use to check to see which model is the best among all the ones that we've built. So this is for model selection. And then our test set is our honest estimate of how the model will perform in the future. Now, what we're going to do after we build our model, and after, first we're going to partition our data, build our model, and then we're going to check the statistics of how our model performed on each of these three subsets. In general, you can expect the training data statistics to look better than the validation data, which will probably look better than the test set statistic. Okay, now why is that? All right, so the training data is what I optimized and tuned my model on. So of course, the model is going to probably look the best on the training data. Now the validation data, if I've built a lot of models, then what's going to end up happening is by happens, chance, and fluke, that certain model structures, certain models will look better than others, not because they're actually going to perform better, but because there's just little fluctuations that it just happens to work out that way. And so our training statistics tend to be optimistic, like truly optimistic. The validation statistics tend to be on the optimistic side, but not as much as our training statistics. And then our test statistics, this is our honest estimate of how the model will perform, tend to be worse than the other two. Now, my experience is that our test set statistics tend to actually be better than the model actually launches in the future. And so keep that in your mind also. So if what I personally use to kind of gauge overfitting is that if I have my training statistic and my test statistic are far apart from each other, if I see a big difference, that's an indication I've overfit. The bigger the difference between my training statistic and my test statistic, the more concerned I am with overfitting. Now, it's possible that the overfit model could actually outperform other models I have. My goal is to predict the future. If a model will perform better than the others on future data, that's the one I want, even if it's overfit. But of course, if it's overfit, that's a bad thing. So simultaneously, we try to juggle a lot of things when we do actual machine learning. All right, so our goal is to take our data, build a predictive model that generalizes to unseen data that we are going to make predictions on. And we're going to call that data our scoring data. Our score data is the data that we actually want to make predictions on. Now, we don't know the truth. We don't know what the target variable on our score data will be. That's the point of the predictive model. And so this will be the data that we use when our model goes into production. So as we go through this, we're going to try and minimize bias, minimize variance, have it as accurate as possible, avoid underfitting and overfitting. Underfitting is nowhere near of a risk as overfitting. If I underfit, typically what ends up happening in real life is that the model doesn't perform as well as it could have, but we tend to know this before we put things into production so we don't get shocked. If I overfit a model, what ends up happening is I think things are going to look better than they really are going to, and then I get smacked in the face hard and heavy, and then I have to tell my stakeholders why things went the wrong way. Not a good position to be in. I've been there. And so the train validation test split is how we set up our data, or we train the model on the training data, check performance on training data, validation data, and test data, and then we compare the statistics on each of these. So this might be accuracy, there might be sensitivity, specificity, depending on the situation I'm working on, maybe AUC, and I look at all three of these to judge, do I have a good model? Which model is the best one to put into production? Now, this really is a cornerstone approach to supervised learning. Classical statistics really didn't touch on this very much. This is really like when data started getting big, this is when this became like the way to go. Before, when data really was a small data, like compared to today, when all data was small data, the statisticians were relying more on theoretical aspects and just an understanding from pencil and paper proofs to guide us on what is a good model, what is a bad model. And so back in the day that made perfect sense because we didn't have the data to chop up and not use all of it for our training data. So something that's important when we take this approach is that I have to have enough data to split out. Let's say I've only got 10 data points to work with. Well, if I've only got 10 data points, I don't have enough to do a train validation test split. Honestly, I'm probably just going to build them first of all, I wouldn't want to build a model with only 10, but it might be really, really necessary if it's a really critical situation and collecting data is very, very expensive. And so those 10, I can't afford to put anything into validation or anything into test. And there I would lean on classic statistics to decide, do I have a good model? Yes or no. When I've got a reasonable size of data, I can go ahead and do the train validation test partitioning. All right, so the training data its purpose is the data I will actually build my model on. Now, I will go ahead and take advantage of having the data and running the statistics on how well, on like how accurate, what the AUC, sensitivity, specificity, all that stuff is on my training data. But that's not really that's like just kind of a corollary I get for free aspect of the training data. The purpose of my training data is to fit the model and get just to take my data, train the model, fit it, and then I've got the model to work with in any way, shape, or form. All right, so here, this is the data that our model is learning on. All right, so let's go ahead and run through some examples. So here I'm setting up my workspace, suppressing the number of digits to be printed, avoiding scientific notation, and I want to suppress warnings because I'm going to be doing some stuff that's going to cause R to bark at me. I understand what's going on. I want to suppress that. I'm making sure I don't have any gunk in my workspace, and I'm going to be using piping. All right, so let's go ahead and take a data set to work with. Now I got this from, I believe, Kaggle. This is the mushrooms data set. This is a classic data set at this point. And you can see that I'm going to be pulling in all categorical columns except for one, which I'm going to omit off of this. Doing this column types, by specifying it, you can speed up the loading of your data by quite a bit. Read R, the package is pretty fast at reading data. This is a decent sized CSV file. This is not the fastest way. data.table is a much faster package, but it has its own nuances, own syntax. I like read R because it's consistent with R more in general. All right, so here I'm going to go ahead and um, go through and convert my target variable to binary. That way I can take averages. And so what I'm going to do to make things faster and easier in my initial exploratory phase is I like to replace categorical predictor variables with the average of the target variable. And this is called categorical smoothing. One thing that's nice about this is that I start with one column of data and I fit my model with one column of data. This is in contrast to dummy variables. Let's say if I had 50 states and I have all 50 states in a column of data for a predictor variable, if I go to do dummy variables, I'm going to have 49 or 50 dummy variables. One column with the lowest informative value level of data results in 49 or 50 columns. I really personally don't like that. So I like to do categorical smoothing. I feel like this is a good choice for modeling in general, but it's also a good choice when I'm doing my first initial look at which predictor variables to keep and get rid of. If categorical smoothing indicates that a predictor variable, a categorical predictor variable is highly informative, then I'm going to keep it along the way. If I've got a lot of variables to wade through, I can decide on which ones to get rid of, which ones to keep pretty easily. And the interpretation is much easier because one column for the original data, one column for the prepared data. So here, what I'm going to do, I'm going to go through and compute the overall mean. And what I'm going to do is I'm going to compute so this is T apply for each column that is a categorical predictor variable column. I'm going to compute the average, like the average of the poisonous, for the target variable. So here in my target variable, a 1 means poisonous, a 0 means edible. And so this computation is computing what is the fraction of poisonous in the data set. And I'm going to replace the levels in the data set with the conditional average. And so this is the computing those averages. This is the overriding of those levels right there. And so now we can see as a first glance, a very nice, if I can go through, compute the correlation between my binary targets, the class, so my binary target is the class column, and I take the correlation with all the categorical smooth predictor variables, and I can get an idea of what I've got. So right here, boom, odor, I can see, hey, odor is one that I'm probably going to want to include in my predictive model. After that, I've got spore print color that's coming up second. And you'll notice it's kind of a big gap between them. Now, something I did wrong, technically, I did Pearson correlation. With binary variables, you don't want to do, from a theory point of view, you don't want to use Pearson's correlation because that is like the straight line correlation, doesn't make sense. But I find that for big data, it works pretty well. And for the purpose of just ordering predictor variables, this is a good way to go pretty easily. Now here, right off the bat, when I look at the stock shape, it's one that I'm probably going to want to kick out. It looks like I don't have much correlation going on there. And I can go through individually and kind of get an idea of what do I want to keep, what do I want to get rid of. All right, so now just to make things easier to interpret down the road, I'm converting all those binary values of 0 and 1 for 1 for poisonous, 0 for edible. I'm converting it back to P's and E's, just so it's just a touch easier. And one thing I like to do to keep my data like well organized is I like to have a vector of all the column names corresponding to their use. So I'll have a vector of all columns that are ID variables, all the columns that a vector of all the columns that are date variables, predictor variables categorical, predictor variables numeric, target variables, administrative ones, partition variables. I'll have a vector for each of these types, and this I find is a good way to keep everything organized for me. All right, so let's go ahead and let's just build a full model, just write out or build a model using cap color and gill color. So let's look to see what we have. We have gill color is here, and cap color, where is cap color is here. So gill color is one of the higher up ones, and cap color is one of the lower ones. And I picked these because they're not going to be perfect. Honestly, Odor does such a good job in this particular example that I really don't want to use it because the model will not look realistic for real situations. All right, so now we can see that as the cap color fraction goes up, we can see how much the log odds are expected to go up. As gill color goes up, we can see how much the log odds is expected to go up. So that that is interesting. All right, so that's just a first initial run, just a quick look. But you'll notice that I didn't go through and do the train validation test split. Let's go ahead and actually start doing that. So here's the first way to do it, is to go ahead and define a column of train validation tests. I'm going to show some other ways using the carrot package in a moment, but this is typically how I do it. I like to have a dedicated column specifying what's what, and so that way I can go back and look in the future. And so I've got train validation tests, and I'm sampling with replacements, number of observations I have to work with, and I typically do even, 1/3, 1/3, 1/3 on my modeling. I hear a lot of people use 70%, 15%, 15%. Whatever you choose is right. At work, I usually have a good amount of data, so 1/3, 1/3, 1/3 works out pretty well. The smaller your training data, the faster the computations will be to fit the model. And so since it's faster, you'll be able to work through your project quicker. Now, when I have less data, of course, for the training, that's a drawback because I'm not fitting the model potentially as much as I would if I had a larger data set. So we have to weigh the benefits and the advantages. I like to have speed on my side as I work through this phase of the modeling, and so I tend to go smaller. All right, and so here are my predictor variables for going forward. All right, so the training data, remember that this is the data that I build the model on. The model is fine-tuned to whatever is in the training data. Now, the validation data, this is the data that I'm going to use to do model selection. So during a real project, I'm going to build a whole slew of models. Now here we're talking about logistic regression. So we do a whole slew of different logistic regression models using different interactions, quadratic terms, doing different data preparations. If it's a larger project where I have a wider range of things, I'll be doing support vector machines, random forest, k-nearest neighbors, anything and everything for this. And after I do that, I'm going to have a whole slew of models to evaluate. Now, what we're going to do is that we're going to use our validation data. So I've fit all these models on the training data. Now I'm going to score the validation data. I'm going to check to see what predictions do my models give on the validation data. And then with those predictions, I'm going to check the accuracy, sensitivity, specificity, recall, precision, AUC, all those things that are of interest to me on the validation data. And whichever model comes out on top, that's the one that I'm going to probably put into production. Now, we're also going to have a test data set in a moment. All right, so now what's going to end up happening is that the training data is going to be optimistic if I take my training data, put it into the models, check accuracy. Because of the fine-tuning aspect on the training data, it's going to be optimistic. Well, the validation data is going to be optimistic also because we're picking the best one. When we pick the best one, there could have just been like some random fluctuations that happen, and those random fluctuations made it so that this particular model came out on top. And because of that, we can't fully trust the validation data. Now, the more models I build, the more models I do the validation check on, the more opportunities I have for fluctuations in the data to cause a model to look really good. And so because of that, the more models I build, the more important my validation data is. Now, our test data, the goal of the test data is to give us an honest estimate of how the model will perform. All right, so the model, when I fit it, only saw the training data. It didn't see validation. And now I've decided, you know what, I'm going to launch this particular model based off of the validation data. And now I know the validation is optimistic. And so I'm going to put my test data into the model or models I'm considering putting into production. And now check the accuracy, sensitivity, specificity, precision, recall, all that stuff, and just get a better estimate of how the model will perform in the future. Now, if I don't build very many models, I can just go train test. I don't need a validation. The more models I build, the more important the validation set is. And so I know plenty of people who just skip over validation, go straight to test and use like basically their test set as their validation set. If you see someone who's not doing train validation tests, they say train test split. They're doing the like validation and test together, and it's only if they're only doing a few models, they're really not exposing themselves to that much risk. But if they've built a lot of models, they're rolling those dice. All right, so here we're leaning on the test set to give an honest estimate of how the model will actually perform. We don't want to launch a model that is going to smack us in the face, right? We want to know what's going to happen before it actually happens. And we're going to take our training statistic, our test statistic. We expect the test statistic to be better than trained. It doesn't always work out that way, but typically. And the bigger the difference between the two, the more that the training statistic looks better than the test statistic, the more I feel I have a risk of overfitting. All models overfit. It's a question of by how much. And this is how you can go and check, have I overfit? Is this okay for me to proceed forward with it? So the models are trained on the training data, and because of just how we do statistics, how we do machine learning, the model is fine-tuned to the training data. It's fine-tuned to the data it was built on. And so it's going to be optimistic, like 100%. Now, the validation set is still going to be optimistic. Why is it optimistic? Well, because if I've gone through and let's say I built 1,000 models, well, the model that looks the best probably has had some random fluctuation in the data that just this combination of algorithm and data ended up looking good, when in the future, if I was to put this into production, it wouldn't look so good. And this is why we need the train, validation, and test splits. Now, the test set is what we're using for our honest estimate, but my experience is that the test statistics are still optimistic. It's just that we hope that it's not too optimistic. So why would things just be different? Well, I'm going to highlight two reasons for that. Over time, things change, right? You get your data that you're going to build your model on. Let's say it's last year's data. Well, things have changed between last year and today. And things are going to change between the time that you build the model, you put it into production, and the model actually makes a prediction. And the longer that time goes by, let's say towards the end of the model, you're going to expect to see a degradation of the performance of your actual model. And so there's a time between that the training data was collected and then you build the model, and then your model starts actually doing the work it was intended. During that time gap, things can change. So there can be changes in the relationship between the target variable and the predictor variables. Also, you can have a change in the data distribution. So let's say that you were working on a data set, and just because of how things were, like there were just like short people in your data. You train your data. The true population at that time was just shorter on average. Then time goes on, and you're in the population you need to make predictions on it's just taller because something happened. Maybe your company became very attractive to taller people for some reason. I don't know, but the distribution of your predictor variables changes, so therefore you get different predictions. Your models always look like the data that they were trained on, and so changes in the distribution of your predictor variables is going to result in a change in the performance of your model. So a subpopulation that wasn't very important in your training data can become very important in the future because they're just proportionately present more. And when that happens, well, your model is not going to perform as well as it did when you did your train test split. There really isn't anything we can do about that except monitor our data and just be aware and know what's going on. All right, so now there's some alternatives to doing train validation test splits. First and foremost, this is train only. Now, I don't recommend this, but there are times that you have to do this. And so let's say I have very, very few observations, and I just don't have enough data to be able to split out into 3 subsets. I have to use all of my data to be able to just build the model. This happens especially if we're looking to like logistic regression, linear regression models, simpler models. And so like we're just not going to go through this. We're still going to look at our train statistic, and we'll use other like classic statistics ways to see, hey, do I have a good model? Now, another thing is just do a train test split. So let's say that I'm only going to build 1, maybe 2 models, then really I don't need to commit so much to the validation. If I'm only building 1 model, the validation step and the test set really aren't going to give me different information. And so I'm not exposing myself to a great risk of fluctuations making the model look different than its performance looks different than what it really will be. And so, I can just, go without the validation step. Now, something that we can do, and different data scientists choose different things. And so some data scientists the opinion is that after I train my data, that is my data, that is my model. I'm not going to tinker with anything. I'm not going to reevaluate anything. Some data scientists will like to, after they select their model and then finalize the model structure, they'll go take their training data and their validation data and their test data after they made their decision of what the model structure will be and refit the model all together to try to get the best fit possible. Now, they could also do this with the training data and the validation data. The disadvantage to this is that you don't have a true estimate of how this model here will perform. But the advantage is that I'm taking full advantage of my full data set for the purpose of fitting the model. My goal is to get the best prediction possible. So I want to use all of my data or use the best data I can get for that. So my opinion is that I prefer to refit. My boss doesn't like that at all. And you know what I do? I do exactly what my boss says because my boss determines my annual bonus. I keep him happy. And it's honestly not going to be a big difference. I've not seen it be much of an issue either way. But I prefer to, after you've decided on a finalized model structure and parameters and data prep, all that stuff, go back, take all of your training, validation, test data, refit. My preference, but other data science disagree. They're not wrong, just a matter of opinion. All right, now something that can come up. Let's say I have an imbalanced data set. Let's say that I have fraudulent data as my target variable. And let's say that I have such few observations in the fraud category that I really can't afford to split that out between train validation tests. All right, so in that situation, something that we could do is take all of our data, all of our fraud cases, and put them in training only and not really get an honest estimate on what's going to happen on that aspect. Sometimes we have to do this. Another option would be to repeat observations across the 3 partitions. This is not a situation you want to be in, but it's an option. If you repeat your low frequency levels across partitions, know that you're going to have some optimism in your estimates. We end up in this position with real life data where we have to make some tough decisions. It's not ideal, it's not perfect, but that's how real projects are. All right, so now let's talk about some ways to select training and validation data. First and foremost is that random partitioning that you can go through, and pretty easy peasy lemon squeezy, where like what I did previously in the video is I used random number generation to say train, validation, and test. I did 1/3, 1/3, 1/3 for the default probabilities. Won't be exactly 1/3 each, but it'll be close enough. All right. And so then that's a way to go about it. If I'm going to use the carrot package for my machine learning, which I highly recommend, when I do this, I need to indicate which ones are in and which ones are out for the validate. So in this, so the carrot package takes care of training and validation for us automatically. Testing is something we have to do manually ourselves. And so we have to specify our training data and we have to specify our validation data if we want to do things manually. And here we're going to get output. There aren't so when we do standard maximum likelihood estimation, logistic regression, there are no special parameters. Like we're not going over grid search or anything like that. There's just one estimate. And so when I use the carrot package, I just get one model each time I run this. Now, the default setting for carrot is actually to do bootstrap. Bootstrap is a sample with replacement on my data. So what we're going to do, let's say I have 500 data points, 500 observations. What Bootstrap is going to sample with replacements 500 observations. All right, so it's with replacement, same number as the original data. Well, because of the with replacement, some observations are going to be repeated, some are going to be not in the training data. Those excluded data points are going to be our validation set. And this is the default setting for carrot. This is also a good choice in a small data situation. And so here I just say method equals boot, or I just leave it alone. This is the default setting. And you'll notice our models end up being pretty tight with each other. I don't end up getting a whole lot of difference off of this because it's pretty similar data. All right, so now k-fold cross-validation. This is where I'm going to partition my training validation data. So here, training and validation data starts in one set, and then I'm going to randomly chop up that data into k partitions. So let's say 3. All right, I'm picking 3 because it's a pretty easy number, but typically we go 5 or 10. All right, on my first split, this is going to be validation. These 2 are training. Then the second run, this partition is validation. These 2 are training. And then when I get to the third one, K, when I get to the kth one, this is the validation. The other 2 are training. And we run through that. And typically, we do this with 5 or 10. What's going to end up happening, the smaller the number, the less data I'm using on each training set, and my things will be faster. So if I do 2-fold cross-validation, it's going to be faster than 10-fold, because with 10-fold, I'm using 9 out of 10 of those partitions. So I'm using 90% of my training validation data, while twofold, I'm using 50%. And so smaller K will be faster for us. So something just to think about. But when it comes to like evaluating the cross validation, what's going to end up happening is that we'll get a better estimate with a higher number. And this is what makes 10 appealing, that we actually start seeing a distribution with that number. Now, repeated cross-validation is cross-validation where we do that random split multiple times. This is my preferred method, by the way. I like to do twofold cross-validation multiple times. And then with multiple runs, I get, so like here, I've got twofold cross-validation, do it 10 times, then I'm going to end up doing cross-validation 10 times. I've got a total of 20 models I'm building. Now I've got an idea what the distribution of what I could expect to see down the road for the accuracy that is. All right, now leave one out, cross-validation. Do not use this unless you're in a small data situation. This is going to be a big problem for big data. If I have 100 data points, what this does is say first time, it excludes the first observation, use all the others. Second time, exclude the second, use all others. Third time, exclude the third observation, use all the others, and run through this. So if I have 100 data points, I'm going to build 100 models. If I have 1,000,000 data points, I would build 1,000,000 models. That's a lot. Now, in multiple linear regression, we have a formula that speeds this up by a lot. We don't have that in logistic regression. And so I want to discourage you from using this unless you're in that small data situation. This is a good choice if I had like 10 data points and wanted to get some kind of validation going. Now, we also have large group one cycle validation. I don't really use this, but it's an option in Caret. Very nice for us. Here I just put the method equals LGOCV. Now, none, this is a situation where we don't run any validation whatsoever. This isn't the best way to go, but this might be a good choice if I have very little data to work with. Now, another option in Caret is OOB out of bag. This is not applicable to logistic regression, but it's an option if you look at the help documentation. This is for bagging models. And so, for example, random forest is by far the best example of this. And so here, when we do a bagging model, we have what's called out of bag. So each time, so in random forest, we do that bootstrap selection of our data on each individual tree. And each time I do this for each individual tree, I have excluded data. So like tree 1 and tree 2 have different included, excluded data on them. So each individual tree includes excluded data differently than the others on their bootstrap set. And on that one, or it might sometimes we don't do bootstrap, it may or may not be, but we do a subset selection. Whatever is excluded is my validation set. And in that situation, each individual tree is evaluated on its excluded data, and then all of the excluded data for each individual tree evaluation is aggregated together, and that's out of bag. I find that this is more optimistic than the validation data typically. Expect it to perform similar to validation. It's less optimistic than the training data. Now, boot 632 is a composite estimate for bootstrapping. It's basically a souped up version of bootstrapping. Pretty cool, pretty interesting. It's a real nice option to execute. Now, optimism bootstrapping. So here, this is comparing the performance on the bootstrap sample with the whole data set as it works through. Another souped up version of bootstrap. Adaptive methods are also available. There's a whole list of other ones I excluded because I feel like the video is getting long at this point. But there are other ways. The ones I've already talked about are the more fundamental methods, and I see those being used more in professional work. All right, now for our test data, so we talk about training data, we talk about validation data. Now we're going to talk about our test data. Our test data, well, how are we going to pick our test data? We can do the random selection like I did previously. Another way is to say, hey, I want to know how this is going to perform in the future. So I'm going to say my last 6 months of data are my test set, and everything before is train validation. And so this is a good way to go if I want to make sure I know how the model is going to perform in the future. Disadvantage to this is that if I take my most recent data and put it in my test set, that data is not being used in my training sets. And so there's some give and take there. Also, another way that we can go with our test set, let's say I know that a certain population of the data is super, super important. Like I have to nail it on this data. Well, I can take that data and use that, select that to be in my test set to make sure I know I'm going to have things perform well. And so possibly I could exclude other, other values, other levels of the data to make sure that I'm fine-tuned and focused on the data that is most important. All right, so for your homework, try at least 3 versions of train validation partitioning on your models. Check to see how it works, compare, evaluate your training statistic, validation statistic, and test statistic, and just, see what you get. Let me know, and, post this in Canvas. That's all I've got for you. Life is short. Do math.